Hello, good afternoon. Welcome to Flexibility Structural Analysis Made Fun and Easy. This is my second video, example 2 for flexibility method in action. My reference example 2. This is the 23rd of May, Monday. So the most important thing about this one is that in this example, this is the first flexibility method that I have done where there are two unknown support reactions. So stay tuned for how you do two support reactions, how you solve it using flexibility method. So the structural analysis made fun and easy. Please like the video and subscribe to the channel for more videos. So we've got example 2, two unknown reactions. So this is again from Megson, the textbook, which I referenced in example 1. So it says example 16.7, determine the support reactions in the 3-span continuous beam ABCD shown in figure 16.17a. It is clear. So if we look at the example, you got 1, 2, 3 spans, 2-point loads, one partial UDL. The spans are each 1 meter, so you got 1 meter between A and B, 1 meter between B and C, and 1 meter between C and D. And so it is. So they start in the solution. It is clear from inspection that the degree of statical indeterminacy of the beam is 2. That's because you've got 2 reactions at A, so that's 2 plus 1. The number of reactions is 2 plus 1 at B plus 1 at C plus 1 at D. So that's 5. 3 equations to solve it. So therefore 5 minus 3 is 2. So it's clear from inspection that the degree of statical indeterminacy of the beam is 2. Therefore, if we choose the supports at B and C as releases, the primary structure is that shown in figure 16.17b, which is the one I'm just circling. We therefore require the vertical displacements VB0 and VC0 at the points B and C. So that's the first. The first step is to release RB and RC, and then you get a simply supported beam with 2-point loads and a partial UDL. So what you got to do is find the the first thing he's doing is finding the displacements in this beam, the release beam, under B and C. These may readily be found using any of the methods previously described: unit load method, moment area method, Macaulay's method, section 13.2. So I'm going to do separate videos on those: unit load method, moment area method, Macaulay's method. And so he's saying VB0 is 8.88 divided by EI, and VC is 0.08 divided by EI. So basically VC is bigger than VB because you've got that, there's the UDL on that side. So this, you could, if you wanted to check what he's done, you can also use standard beam deflection, and then you can add them up by superposition. So the deflection at B and C could be, you could use a beam with 1-point load and then find the deflection, then add another point load, find the deflection, and then add that UDO and then find the deflection, and you'll still get the same. So I haven't done that. I haven't shown how that's calculated, but I'll do that in a separate video. So we now require the flexibility coefficients A11, A12, A22 and A21. So that's basically this is like we're gonna put point load at B and point load at C, just like he has drawn it out in diagram C and D. Point load at B 1 down and point load at C 1 down. I actually think it's easier to understand it if it's going upwards, but I just copied his one. I mean, he's copied his one here on my one. Yeah, I've copied his one. So you got point load at, so for example on his diagram 16.17c, he's got a load of 1 at B. So you've got when you've got a unit load of 1 at B, then you've got to find the deflection at B and the deflection at C. So That's what he's calling. He's calling that A11 and A12, and A22 and A21. So the coefficients A11 and A21 are found by placing a unit load at B, as shown in figure 16.17c, and then determining the displacements at B and C. Similarly, the coefficients A22 and A12 are found by placing a unit load at C and calculating the displacements at C and B. Again, any one of the methods listed above may be used. So there is another way. I'm also going to check this by using. You can use like various tables, or from Steel Designer's Manual, I think it is. It's not coming up, but you can check what his deflected. Check what here it is. So look on this diagram. 7 beam simply supported and its concentrated load P at any point. So you should get that. I'm going to do another video on this, but you should get that Y equals what he said. I do a separate video on that. But it's just double checking that he said on here. However, from the reciprocal theorem, section 15.4 A12 equals A21, and from symmetry A11 equals A22. Therefore, so that's just because it's basically hand. It's like left. This is a left hand one, point B, and this is a right hand one at point C. It's because it's just symmetrical. Therefore it is only necessary to calculate the displacements A11 and A21 from figure 16.1c. These are A11 equals A22 equals 0.45 EI. So that's basically the deflection at B when you got point load at B. It's 0.45, and when the deflection at C when you got point load at C, 0.45 over EI, and then A21 equals A12 equals 0.39. So the deflection at C when you got point load at B is 0.39 over EI, and the deflection at B when you got point load at C is 0.3. So that's the same. So then you can get your two simultaneous equations. So the total displacements at the support at the support points B and C are 0, so that VB0 minus A11 R1, that's R. R1 is basically RB, and A12 RC equals 0, 1. VCO minus A21 R1, also RB, minus A22 R2, which is RB, RC, equals 0. So then you've got your two simultaneous equations. Or substituting the calculated values of VB0, A11, etc. in equations 1 and 2 and multiplying throughout by EI, you've got 8.88 minus 0.45 R1 minus 0.39 R2 equals 0, and 9.08 minus 0.39 R1 minus 0.45 R2 equals 0. So that's equation 4. So then it goes, note that the negative signs in the term involving R1 and R2 in equations 1 and 2 are due to the fact that unit loads were applied in the opposite direction to R1 and R2. Solving equation 3, we obtain R1 equals RB equals 8.7 kilonewtons, R2 equals RC equals 12.68 kilonewtons. The remaining reactions are determined by considering the statical equilibrium of the beam. That's basically all vertical forces equal RA plus RB, adding up all the vertical forces, that should equal to 0 with the reactions. So RA equals 1.97 kilonewtons, RB equals 4.65 kilonewtons. In example 16.5, so that's basically the solution of it once you solve the simultaneous equations. So I'm going to do a separate video on simultaneous equations to refresher. In example 16.5 to 16.7, we have assumed that the beam supports are not subject to vertical displacements themselves. It is possible, as we have previously noted, that a support may sink so that the right hand side of the compatibility equation 8, 9 and 10 in example 16.5, equation 2 in example 16.6, and equation 1 and 2 in example 16.7 would not be 0 but equal to the actual displacement of the support. In such a situation, one of the releases should coincide with the displaced support. So this is now just closing up. It is clear from example 16.7 that the number of simultaneous equations of the form of equation 1 and 2 requiring solutions is equal to the degree of statistical indeterminacy of the structure. So this is just notes on the technique. For structures possessing a high degree of statistical indeterminacy, the solution by hand of a large number of simultaneous equations is not practicable. The equation would then be expressed in matrix forms and solved using a computer-based approach. Thus, for a structure having a degree of statistical indeterminacy equal to n, there would be n compatibility equations of the form v10 plus a11 r1 plus a12 r2 plus plus a1n rn equals 0, vn 0 plus an r1 plus an 2 r2 plus plus ann r1 equals 0, or in matrix form. So you've got v1 to vno equals a1 minus a11 a12 etc. r1 to rn. Note that here n is ns, the degree of statistical indeterminacy. The subscript s has been omitted for convenience. Alternative methods of solutions of continuous beams are the slope diffection method described in section 6.9 and the iterative moment distribution method described in section 16.10. The latter method is capable of producing relatively rapid solutions for beams having several spans. So that's basically the solution. The first example that I've done using with two supports unknown for flexibility method, and I'll do some more videos to go with it. So that was flexibility method in action and MyRef example 2. Please like the video and subscribe to the channel for more videos. Thanks for watching.